scholars. I hope that you and your family and loved ones are doing well. We at SEO are thinking about you every day. We care about you, and we're sending our best wishes. So usually in an SEO math class, we all rely heavily on your knowledge, your thoughts, and the ideas that you bring into the classroom. And there are many opportunities for you to talk with your classmates about an idea, or to come to the board, to share what you're thinking, to ask questions, and just in general to solve problems together. And so although much of these activities aren't possible when you're watching a video, I still encourage you to try to watch this video as if you were in a classroom actively. And so what this means is to take out your workbook or a notebook while we go through the lesson together and take notes in it, just as if you were in a classroom. Feel free to pause, rewind, and watch parts of the video a second time if you're confused. And make a note of things that you're still confused about after this lesson so that you can ask your instructor. All right, sounds good. So let's get to it. So during the last lesson, we talked about different characteristics of graphs. So we talked about intercepts, we talked about if graphs are increasing or decreasing, and how to identify points given information and function notation. So this lesson is also about graphs, and we're going to talk about transformations. So you've likely seen or heard the word transformation in a geometry class when we talk about sort of rotating or reflecting or dilating different geometric objects. So it could be a triangle or a square or a rectangle, something like that. And it's basically, it's very similar here, only here we're talking about functions. So we're talking about shifting, scaling, and reflecting functions. So we're going to go through sort of all the different ways that we can think about transforming functions, the graphs of functions. A big idea here before we get started is that you are likely introduced to functions as sort of input-output machines, right? So if you have a function, you have an x value, right? And then you sort of like put it into the function machine, right? The f machine, and then out comes the y value. And we sort of did it point by point, right? So if you have another value, you can get another value. And if you have enough of those, right, you can create something right here. Like we have a table of values here for the graph or for the function y equals absolute value of x. And with the table of values, having, doing this input-output machine enough times, you can actually find points that are on the graph of y equals absolute value of x. So this is definitely one way of interpreting a function. Another way, especially if we're dealing with the graphs of function, is to interpret it as just an object. So here is this graph that looks like a V, and when we interpret it as an object, we can take the whole thing and move it around. We can shift it up, we can shift it down, left, right, we can flip it, we can do anything we want with it. So it's a different way of sort of viewing this function. The function is a very challenging and important concept, plays a really large role in higher level math in college. So I just wanted to highlight that here. Okay, so let's take a look at example number 1. So here we have the graph of y equals absolute value of x. And a function table with the input-output pairs. So again, just a reminder, the absolute value function is telling you the distance from 0 on a number line, and so that means that positive values, right, if here's a number line, right, if I'm talking about here's 0, and I say here's -3 and here's +3, since absolute values is measure of distance, the distance from 0 in both cases is a +3. Since distance is always positive, and so that's why the absolute value changes negative numbers to positive numbers and keeps positive numbers the same. So for example, we have the absolute value of -2 is +2. That means when x equals -2, y equals +2, and there's that point right there. And we could do the same thing with the point 1, 1, which is right there, and there's that point right there. So basically we have the, if we have the collection of all of these points, right? So there's a point, there's a point, there's a point. We can draw a line through all those points, and every point on that line solves this equation. Every xy coordinate pair solves that equation. All right, so let's keep going. We're asked to sketch a graph of y equals absolute value of x plus 3. So we're going to do that in red. And to sketch a graph of y equals absolute value of x minus 3. So we're going to do that in blue. Okay, so first off, let's take care of this red graph. So we have here our original graph, our initial graph of, right, the sort of, we can call it our parent graph if we want. This is sort of our starting place, y equals absolute value of x. And we want a graph, it's the same thing, only we're adding 3, right, to all of the y values, right? We're saying whatever output you would have gotten here for y equals absolute value of x, right, let's just add 3 to it. So for example, let's take a look at just one of these points. So if x equals 2, so let's say, what does it look like if x equals 2? Then the absolute value of x, what would that look like? Or actually value of x plus 3, because that's what we want to graph. What would that look like? Well, if x is 2, we'd have the absolute value of x plus 3 is the absolute value of 2 plus 3, which is equal to 2 plus 3, which is equal to 5. That's telling us that the point 2, 5, now we know based on that the point 2, 5 is on this new graph, right? We just took 1 point. So basically what we see is, we see that it used to be that the point 2, 2 was on the graph, right? When we added 3, the point 2, 5 is on the graph, and I'll be darned if this isn't just a shift of 3 up in the vertical direction, right? We can do the same sort of xy table and find some more points, right? But really, essentially what we're doing is we're taking every point on this initial graph and we're shifting all the points up. So 0, right? If x is 0, y becomes 3 now, right? If x is -3, y becomes 6, so forth and so on. And if we take all those points and shift them up by 3, our new graph is going to look something like that, more or less. So here we have our y equals absolute value of x plus 3 graph. It's a shift 3 units up. Now I bet we can guess what this absolute value of x minus 3 is going to look like. Again, we can try plugging in some values for x. Maybe the most interesting one is if we plug in the value for x equals 3. So in this case, instead of, we could say y equals absolute value of 3 minus 3, and that's just going to equal 0, right? So in this case, we're taking this initial point. So it used to be in the original graph that the point 3, 3 was on the graph, and we're going to shift it down, and now we have the point, right, 3, 0 is on the graph. And we'll do the same thing for all these points, just like we did when we shifted up, and we can sort of sketch a graph right there. You know, roughly this is what this one's going to look like, more or less. And so this one right here, we says y is absolute value of x minus 3, and this one is going to be our y equals absolute value of x plus 3. So here we have seen some different ways to do vertical shifting of a function. All right, let's keep going. All right, so here we're being asked to sketch a graph of y equals absolute value of the quantity x plus 3, as well as y equals absolute value of the quantity x minus 3. So these are going to be horizontal shifts as opposed to vertical shifts, and we're going to see in a minute why that's the case. And so let's start with this one. Now we might think as a safe or a sort of initial assumption might be, well, I see it's a plus 3. So then likely we're just going to take the graph and we're going to just shift everything plus 3, right? Because it's a plus 3 right there. And we'll just sort of draw the graph, something like that, and be done with it. So this is incorrect. This is actually not how it works. And perhaps one way of seeing why this is actually not a horizontal shift to the right, but it's actually a horizontal shift to the left, is to take the point 0, 0, which is on our original graph, and think about where in this transformation, where does that point go to, right? And so what we want to do is we want to think, I'm just going to do some notes over here. We want to think, what value of x, what number could I put in there to get out a y value of 0, right? Because again, this point, right, this point is 0, 0. It has a y value of 0. So the answer is, and if I want to get out a y value of 0, I have to put in x equals -3. And that gets me back to my function value, right? The y values are the function values. So that means that the point -3, 0 is on my graph. When that means that this point right here, our origin point, is actually shifting to the left. And we can do a similar type of argument with different points on this graph. However, by this point, I hope we see that if one point shifts over, the entire graph is going to shift over. So every point is going to follow that origin point, and more or less this is what our shift is going to look like. So this right here is y equals absolute value of x plus 3. So a plus 3 when it's inside sort of the function input is actually going to be a shift to the left of 3. Now, I bet we can guess what absolute value of x minus 3 looks like. It'll be a shift to the right, but let's just take a quick look at what that would look like. Just again, considering this origin point right here, I think it's helpful to see. So here, the question we're being asked is, if y equals 0, right, what value of x could I plug in to make that value minus 3 equals 0? And the answer is clearly 3 is going to work. So that means, right, since that 3 is that x value, that y is, or that 0 is that y value, it means that the point 3, 0 is on our new graph. And so, let me just get rid of that 0, 0 right there. And so, we're able to say this point right here is actually shifts over to 3, 0. And where that one point goes, the entire graph follows. So here we go. So it's a little messy, but this one right here is going to be y equals absolute value of x minus 3. Shift to the right. Okay, let's keep going. So in addition to shifting, we can now shift vertically, up, down, horizontally, left, right. We just did it. We can also bend and stretch graphs. So let's see what that looks like. So here again, we are always starting with our parent graph of y equals absolute value of x. And we're being asked what happens if I put a 2 in front of it, right? And I multiply everything by 2. And really what you're doing there, we can do that one again in red. So really what we're doing here is we're taking each one of these function values, these y values, and we're multiplying it by 2. That's what it's telling us to do. So instead of the point 1, 1, we're going to have the point 1, 2. And we can see that because if I plug in 1 here, I'm going to get out 2. Instead of the point 2, 2, we're going to have the point 2, 4, 3, 6. And same thing is going to happen 0, 0, because 2 times 0 is 0. Same thing is going to happen on this side of the graph right here, 3, 6. And so essentially what we've done, the role that that 2 is playing is it's basically, yeah, those are kind of straight. It's basically as if you took the graph and you sort of put a hand on one side, a hand on the other side, and sort of smushed it together, right? That's sort of what this is doing, this 2. It's making the graph more narrow. It's sort of, yeah, making it more narrow. Okay, so conversely, we can think about what the value of 1/2 is going to do for us. Let's do that in blue. And 1/2 is basically telling us that every point, every y value that you used to have, take half of it, right? So instead of the point 1, 1, we're going to have the point 1, 1/2. So a little hard to see. Instead of 2, 2, we're going to have 2, 1, right? 4, 2. And we can see sort of where this is going. We're essentially taking that graph and we're making it wider, right? So this one right here is going to be our 1/2 absolute value of x. And this one right here is going to be our 2 absolute value of x. And that should make sense. We can also sort of see this as a continuation, right? So this is a 2. This, even though we don't write it, right, there's always an invisible 1 in front of here. So we're going from 2 to 1 to 1/2, right? And we're going from narrower to a little bit wider to a little bit wider. And we can even imagine what with, right? We're going from 2, 1, 1/2. We could even do y equals 0 absolute value of x, which is just, right, y equals 0, which, I'll be darned, is just this line right here, right? This is the x-axis, is the line y equals 0. And so we can see that continuation from 2 to 1 to 1/2 to 0, we're taking this graph and we're sort of making it wider, wider, wider until, oh, it gets to be flat. And believe it or not, we could even go even further, which we're going to see in the next problem as well, and get into what would it look like if I had a negative, right? -1, -1 absolute value of x, and it will continue, right? -1 is actually going to be flipping it all the way down. So let's take a look at what that looks like in the next problem. All right, example number 2. So here we've switched the function, but the same sort of patterns that we notice are going to be the same for any function. So here we have the graph of y equals square root x, as well as a function table with a few input-output pairs. So just a couple things to notice. One thing is that when x values, as we see right over here, when x values are negative, the function value is undefined because a square root of -9, for example, this is not a real number. In order to calculate this, I guess, or to simplify this, or to interpret this, I guess would be a better word, we're going to need the imaginary number I, which is the square root of -1, and we are not talking about that today. So that means that that this function is not defined for any negative values, and that's why in the graph you see all over here, everywhere here, x is negative, but the function is not anywhere in quadrants 2 or 3. So that's just one thing to note. And then, just like any old function, we have an input, we have an output. We can, from that input-output, find an xy point that's on the graph, and there's that point. So let's keep going. So this next question is asking us to take our parent graph of the y equals root x and sketch a graph of y equals negative root x. And what would that do? Well, in the same way that the value of 2 or a half sort of said basically take all the y values and multiply it by that, this value of negative, supposed to write it really a -1, it's basically telling you to take all of the y values and flip the sign, right? So if it's positive, it should be negative, and vice versa. Now in this case, in the function, the original function, all the y values are positive, right? They're all in this quadrant number 1. And so all that negative square root of x, here, I'm just going to write it over here so we can take a look at it a little bit easier. So all this negative sign is doing is it's saying whatever that output used to be, so it used to be the point, right, 4, 2 used to be there. Let's flip the y value. Instead of 4, 2, let's make it 4, -2. So here, we're not really shifting up or down. What we're really doing is we're taking every one of these values and we are reflecting in them. There's a reflection across the x-axis. And that is what this negative sign right here is doing. So we can follow points. We can say the point 9,3 is now the point 9, -3. We can do it point by point, but really we end up getting this graph right here. So this right here is y equals negative root x. It's a reflection over the x-axis. Okay, let's keep going. How would we reflect over the y-axis, I wonder? So we're being asked to sketch a graph of y equals square root of negative x. So let's just write that a little bit bigger here. Y equals square root of negative x. Okay, and it may be helpful here to just sort of take a point and see what happens to a point. So let's take the point 4, 2. So initially, in y equals root x, we had that 2 was equal to square root of 4, right? This is where we had the point 4, 2. That's where it came from. So there it is. And so here, we want to think, if I want the y value of 2, again, I want to get the same function value, what number do I need to put in here for x in order for the square root of it to be equal to 2? Well, I know the square root of 4 is equal to 2. So how can I get 4 underneath the radical, underneath this square root sign? There you go, right? A -4. So this means that the point -4, 2 is going to be on our new graph. Where's the point negative 4, 2? There it is. And we can do the same with a couple other points, but let's just sort of get to the punchline here. We have a reflection over the y-axis. Okay? So every point over here is transformed by being reflected over the y-axis. So that's the difference, right? I know in the earlier problem, we had a reflection over the x-axis. It looked something like that, and this was how it looked to be, right, if the negative was on the outside. That's the difference if the negative's on the outside versus if the negative is sort of on the inside of what the function is doing. So we're going to take a minute to summarize that, and so we can sort of make sense of all the things we've learned today. All right, so this table looks a little intimidating, so let's make sense of it. So we initially started this lesson talking about vertical shifts. We said that if we add sort of a 3, right, to a function value, it's basically shifting it up. And if we subtract a 3, it's shifting it down. In this column right here, we're being given sort of the generally what it would look like for the general function f of x. So this is a general function. And these right here are specific, right, obviously, specific functions. So we have our absolute value of x that we spent some time talking about for the vertical and horizontal shifts. So that's why they're all filled in here. We also scaled. We made it narrower and wider. And then we talked about reflecting over the x and y axis. We used the square root of x. We also have a linear function here. We have a quadratic function. We have an exponential function. And we have our rational function, or the graph is a hyperbola. Okay, so what would it look like for these specific functions? What would vertical shifts look like? Okay, so I'm going to fill out a couple, and then we can sort of see how we can fill out the rest. So here, if we want to say, if I want to shift the square root of x up by 3, it's sort of simple. I just go square root of x plus 3, right? And we're done. 2x plus 3, x squared plus 3, and let's just keep going. 2 to the x plus 3. These are all shifts, and 1 over x plus 3. I'm going to let you fill out the minus 3's. It's the same pattern, as you can imagine. Okay, we also talked about horizontal shifts. So in this case, note the difference in the form. I'm going to do this in a different color, right? So here we have our f of x plus 3, and here it's f of the input is x plus 3, okay? So we saw how this looks differently in the absolute value function. Let's take a look at how it would look for different functions, different types of functions. So here we're going to do the square root of the quantity x plus 3. You see how this one is different from this one right here? Great. So the same pattern is going to keep going. Definitely encourage you at this point, if you feel comfortable, to fill in the rest of this table right here. And I'll do it right now as well. So instead of 2x plus 3, it's going to be 2 times, right? Our x is turning into x plus 3, that quantity. Here, we're going to do x plus 3, all of it squared. You see the difference here? Here, we're going to do 2 to the power of x plus 3. And here, it's going to be 1 over x plus 3. So this is a subtle but important difference when we're thinking about interpreting functions, different types of functions. I'm going to leave you to fill in these boxes right there. So scaling, I'm just going to do a couple and leave you to fill them in as well. This would look like a 2 times square root of x. This would look like a 2 times 2x, and so forth and so on. Just multiply by 2, and same thing, multiply by a half. And let's talk about reflecting over the x and over the y-axis. Here, right, we're talking about our negative root x, or it's negative absolute value of x, and here we're talking about the absolute value of negative x. That's the difference. Same thing is going to be here. Now here, we're talking about 2x, right? This is a negative 2x. It's still a linear function, and this is 2 times negative x. So it's actually the same, and that's because if you take the graph of y equals 2x and reflect it over the x-axis and reflect it over the y-axis, you're going to get the same graph. So it's kind of interesting there. And x squared, we're going to have a negative x squared, and this one's kind of interesting as well. I'm going to spend a little time on it. We would say this is the quantity negative x squared. So let me come back to this one right here, and we're going to come back to it. Let's just finish filling this out. Here we're going to have negative 2 to the x, and here we're going to have 2 to the negative x. Hope you see how this pattern, how we can fill this entire table out. And here we're going to have negative 1 over x, and the identical thing here is 1 over negative x. So these two are the same as well. That's because this graph, when you reflect it over the x-axis or over the y-axis, you get the same result. So let's just take a quick look at the functions y equals x squared and reflected over the y-axis, right, which was y equals negative x, that quantity squared. So as a reminder, right, here's our x, here's our y, here's a beautiful quadratic, y equals x squared. Look at that. So symmetrical. Here's our y equals x squared. And this right here, we said this was a reflection over the y-axis. So check it out. If this is my original graph, and I take this part of the graph and I reflect it over the y-axis, I get this part. And same thing, if I take this part right here, this part right here, and I reflect it over the y-axis, I get this part. So in fact, a reflection over the y-axis, you just end up with the exact same graph. Algebraically, this also makes sense, right? Because if I say that the value of negative x squared, that's negative x times negative x, which is x squared, which is exactly our original graph. So sometimes it could be that the transformation itself leads to the same graph. And so I just wanted to highlight that when we were comparing right here. This is what we were comparing, reflecting over the y-axis, this baby right here, and then our original graph. So this is a way where the transformations on the graph and the algebra, they match up. And they always do, right? Because I mean, math is consistent. It's the nice thing about math. So in general, let's finally sort of summarize what we've learned. So the transformation of y equals f of x to y equals a times f of x minus h plus k. So this is, again, in general. That's why there are so many variables. So it does three things for you. The first thing is, here we'll use different colors. The first thing is that the a value there is going to scale by a factor of a, right? We saw that with the 2 and the 1/2. And the h right here is going to shift h units to, in what direction? So remember, even though it looks like it's a negative, you'd think, oh, it's to the left. This is actually to the right. And this is assuming here that h right here is a positive number, right? If h is negative, then this becomes really x plus a positive number, and then it's to the left. So okay, so we're just assuming that. And then finally, we have our k value right here, and the k is going to result in a shifting of k units, assuming k is positive, up. And if k is negative, then it would be down, of course. And so that's basically what we've seen today. So thanks. I hope you enjoyed the video, and stay safe.